Hello everyone! It's a pleasure to present to you our work on axion emission from strange matter in core collapse supernovae. First of all, it is important to know the motivation to study the QCD axion, which is one of the best motivated particles beyond the standard model. Firstly, experimentally, there is a tiny CP violation in chromodynamics, but theoretically there is no explanation in standard model. But the QCD axion gives a mechanism to solve this problem, named the strong CP problem, by a U1 symmetry. Secondly, as you know, one of the most important problems in actual physics is the dark matter problem, and the QCD axion constitutes a viable candidate to solve this major problem. Finally, the QCD axion may address other problems, for example the hierarchical flavor structure of leptons and quarks. To understand the QCD axion, it is important to know how the axion interacts with matter, in our case with quarks. In the interaction, you can see three parameters in KL and KR matrices. And an important fact is that the axion interacts in a derivative way, therefore all observables will be proportional to the square of external momenta divided by Fa, the axion constant. But for QCD axion, Fa is very large, bigger than 10 to the 9 GeV. Therefore, for ordinary processes where the external momenta are around few GeV or less, this quantity will be very small, which means that at colliders, where we need energy measurement, the QCD axion is generally unobservable. But if we change our point of view with time measurement instead of energy measurement, we can obtain information about QCD axion. The idea is to use astrophysical observations because dense and hot enough astro objects may radiate axions sufficiently to cool down faster than expected from standard model with neutrino, for example. For us, an important astro object is supernovae because in the core collapse picture, supernovae stand out as QCD axion probes. The idea is to use the astro observation of SN 1987A and the measurement of the neutrino burst associated to it, which can strongly constrain sources of cooling beyond standard model. Generally, the bound used is the Raphael bound, which is the saturation bound of exotic sources of cooling. For us, the axion emissivity, Qa, is smaller than the neutrino emissivity, Qnu, with the emissivity in a particle being the power energy per time radiated via the particle per unit of volume. This means that to use the Raphael bound, it is crucial to know how we can estimate the axion emissivity and the neutrino emissivity. For the neutrino emissivity, we can't directly measure this quantity from observation. We can only measure the time of the neutrino burst and estimate the mass and the density of the core. Using these quantities, we can have an estimation of the neutrino emissivity, but it is a crude approximation with an 100% attached error. For the axion emissivity, we need to do the calculation. We see the integral of an element of phase space times the axion energy times the square of the absolute value of the Feynman amplitude of the process times the distribution function of external states. To compute this quantity, we need to do some common assumptions. Firstly, we don't know what are exactly the distribution function on the core, but the more rigorous one comes from the ideal gas assumption with the Fermi-Dirac and Bose-Einstein distribution, which is used. Secondly, to take into account the in-medium effect, we use the mean field framework by replacing the vacuum quantities by effective ones for chemical potential, mass, and energy. To compute the axion emissivity, we need to choose processes, and in the literature, the most studied bound come from the nucleon Axion-Strahlung, with 2 nucleons give 2 nucleons plus an axion. But recent literature suggests that the Compton-like processes, pion nucleon give nucleon plus axion, may be the dominant processes. You can see in Lilaital plot that the axion luminosity, which is linked with the emissivity, is bigger for Compton-like processes than for nucleon Axion-Strahlung. And in Carranza et al., you can see that the bound over the axion-nucleon couplings are largely better if we take into account also the Compton-like processes. In literature, it is also mentioned the lambda decay into neutron plus axion, but the current literature mainly focuses on first-generation quarks, and for the moment, each type of processes is used to constrain a complex independently of others. Here, the nucleon-nucleon axion or nucleon-lambda axion couplings, and there is no general study in the previous literature. An important question is the role of matter beyond the fourth generation, because the mass gap between nucleon and halpion is small as between pion and kaon. Therefore, in our work, we perform the first study of axion emission from strange matter within supernovae. We need to prove that our work is robust with respect to two modelizations, the axion matter modeling and the supernova core modeling. For the axion matter modeling, we use a consistent effective field theory framework, which I will explain in a few minutes. For the SN core modeling, we consider different equations of states and different values for the thermodynamics parameters. And this because we don't know exactly the SN core properties. The variety of scenarios allows us to see if our results are general. In our study, we compute the axion emission from the full meson and baryon octets via the Compton-like processes with an initial baryon plus a meson give a final baryon plus an axion, and the baryon decay processes with an initial baryon gives a final baryon plus an axion. A very important thing to have in mind is that the emissivity is an additive quantity, which means that all processes contribute positively to the total emissivity. Therefore, even if the baryon or meson fractions are small, the large number of processes, bigger than 100, gives a relevant constraint. Previously, I showed you the axion-quark interaction, but in supernova the quarks are hadronized. Therefore, we need to know how the axion-quark interaction change at low energy to give the axion-hadron interactions. And a consistent way to formalize that is the QRL perturbation theory plus an axion, which is an effective field theory of the chromodynamics. The idea is to use the global symmetries encoded in the left and right-handed Noether currents depending on the mesonic and baryonic fields to fix the interactions, and the axion-hadron couplings, labeled by XL and XR, are parameterized unambiguously from the fundamental axion-quark couplings. Therefore, if we know perfectly the axion-quark interaction, then we know perfectly the axion-hadron interactions. It is important to know what are the couplings that we can find bounds with emissivity. First, instead of using the left and right coupling, we will use the axial and vectorial ones, and by charge conservation and hermeticity, we have 10 free parameters. But the diagonal vectorial couplings are unobservable for strong interaction. They are observable only for weak interaction, which is largely suppressed. Moreover, for the absolute value of the off-diagonal vectorial coupling, the bound inferred using axion emissivity is less stringent than using the non-observation of kaon decay into pion plus axion. And in addition, the phase of off-diagonal couplings are unconstrained by axion emissivity for our processes. Therefore, at the end of the day, the axion emissivity is able to constrain 4 couplings, the diagonal axial and the absolute value of the off-diagonal axial. I show you an example of scenario. The plots are labeled by the k-couplings. The diagonal plots are histograms for each couplings where the others are marginalized by a one-dimensional projection. And the off-diagonal plots are the point passing the Raffel bound to see the correlation between variables. The theoretical scenario is named agnostic, which means that we don't assume any theoretical properties for the couplings and we only use bound inferred from data, which are 3 for KY1, 2.5 for KA22, and 50 for KA23. And for the SN core modeling, we have two alternative equations of states, dd2y and SFOI, with the main difference is the strangeness constant. For this plot, the equation of states is dd2y, and the thermodynamics parameters are the temperature, the baryon density, and the charge baryon fraction, which have specific values for this scenario. The red color is for the decay processes, the yellow for Compton processes, and the blue for both of them. The main conclusions of this kind of plots are that the axion emissivity can directly give the bound over Ka23, principally due to the decay, as through the Compton contributes slightly, and the emissivity implies non-trivial correlation between the diagonal couplings due to the Compton processes. Now I'll show you the table of bounds depending on the SN core modeling. The axion emissivity increases with the temperature and the baryon density. Therefore, if the temperature or the baryon density increase, then the bounds are better. For Ka23, the bounds is order 0.1, which is a very significant improvement from the literature values of 50. And for Ka33, The axion emissivity can't directly bounce this value, but using the data from isolated neutron star, we can constrain KY1 and KE22, and this bound transferred to KE33 by the correlations due to the axion emissivity. The bound is between 3 and 9 depending on the scenario. An important thing to have in mind is that we talk about the QCD axion, not a generic ALP. If we apply this result to an ALP with a mass around 1 MeV or less, Fa will be divided by 10 to the 3, which means that the Ka23 bounds will be rescaled from 0.1 to 10 to the minus 4. To conclude, the supernovae are excellent probes of fundamental physics, especially for well-motivated standard model extensions. And the supernova probe axion interactions not only with ordinary matter but also for beyond first generation. And a progress in the understanding of the sources is necessary to go beyond the crude estimation due to the neutrino emissivity. And for Outlook, if we want to compute the Axion-Strahlung for the full baryon octet, it is important to have a better understanding of these processes to generalize it. We can also further explore the thermodynamic dependence. I mentioned these 2 points because we work directly on it, but of course there is a lot of things to do. I now finish my presentation. Thank you for your attention.